talk about some black hole. So let's just start.
Yep. So hi everybody. Thanks for the invitation. So yeah, I will talk about some aspects of black hole phenomenology, in particular primordial black hole phenomenology, but also other types of black holes that will be mentioned, and in particular about their relation with dark matter searches. So I will focus a little bit on the accretion of baryonic matter onto these objects, and also about the possibility to have spikes of overdensity of dark matter around compact objects. So that's why this title, Dark and Shiny Dresses around black holes. Yeah, so let me start with some context. So let me just start by flashing what are the black holes that we know about. So the black holes that we currently observe. We range from stellar mass black holes that we observe, for example, when they merge and emit a gravitational wave, or when they accrete gas from a companion star and form what we call an X-ray binary system. Then we know black holes that are way more massive, up to millions of billions of solar masses, and they're typically sitting at the center of galaxies, and we observe them up to cosmological distances, and these are called supermassive black holes, typically. And then, we may have a population in between, which are typically called intermediate mass black holes, so ranging from like hundreds of solar masses up to millions of solar masses. This is a little bit of uncharted territory. We have very little observation in this mass range. But yeah, there was a very nice recent detection of a merger event by LIGO and Virgo in September, in which the collaborations could really see the formation of an intermediate mass black hole via merger of two already quite heavy stellar mass black holes. So we are already starting to get into this intermediate mass range as well. And the connection with dark matter searches is one obvious connection is that black holes, some black holes are that could have formed in the very early universe are a dark matter candidate themselves. So besides the black holes that we already know that are from astrophysical origin, we may have another population of black holes of primordial origin that could have formed very early in the history of the universe. And this is not a very new idea. It was already proposed in the early 70s, actually, but it was recently reconsidered in the dark matter community. So you can see that this is the heaviest, if you want, dark matter candidate ever proposed. And the idea is that some density fluctuations in the early universe that may originate during inflation can collapse and form black holes deep in the radiation era as soon as the scale associated to the perturbation re-enters the horizon in the early universe. And these objects can span a very wide range of masses, and if they are massive enough to be stable over cosmological scales, they can be a dark matter candidate. So
Daniele, sorry,
yes.
Are you showing transparencies already? Because I still see the very first one.
Oh yeah. Oh wow. I see the sharing is. Oh now. Oh, okay. It was the sharing of the screen was in standby for some reason.
Okay.
But what's happening now? Now it's in standby again. Now it's green. You are in share screen. Now you can see the screen, right?
Now we can see everything.
And now?
Now we see introduction black holes.
Oh no. I don't know what's happening. So if I do full screen, the sharing stands by.
This happens sometimes with Zoom. Yeah.
Okay. I never. Okay. So maybe I leave the slide like this.
I think maybe it's okay.
But this may happen. I've never seen this effect. I don't know what to do actually, because it's if I do full screen.
Maybe you can try and go stop sharing, go full screen, then share that screen.
Yes.
I don't know if that'll work, but it's
stop sharing, keynote, full screen, and then let's see. Not sure. Let's see. Share screen, keynote. Okay. What about now?
No, it's just the.
Weird.
But this
No
is
idea.
this is fine. You can see everything. So.
Okay. So let's
Read
Or you can use some PDF file if you don't need some animation.
there is actually there is a nice animation at the end.
Okay.
Oof. No, I don't know. Let's keep. Wait. Let me see. Review. No, I don't. Oh, maybe. Instead of slideshow, view full screen. Oh, that's great. It's the problem is with slideshow. It's better. Yes. Okay. Good. So yeah, maybe I go on like this, right? Okay.
Okay, by me.
Yep. So okay. So let me introduce you some scientific questions that are connected to this topic, to this interplay between black holes and dark matter. So we want to understand whether black holes of primordial origin can be all the dark matter in the universe, can be a part of the dark matter in the universe, and what are, if it's part of the dark matter, what are the consequences of this? And then we want to understand if this channel of detection based on observing the radiation emitted by the gas accreted onto black holes is a viable channel of detection, if we can get upper limits on their abundance with this method. And this is the first part of the talk. In the second part of the talk, we want to consider whether we can detect like overdensity of dark matter around intermediate mass black holes. So in this case, I'm not asking myself whether primordial black holes are all the dark matter in the universe. I'm asking whether black holes that we know, we probably know that exist, can be a portal to detection of the dark matter. So can be used as a tool if you want to detect dark matter, whatever is your preferred dark matter candidate. So two different types of questions. So regarding the former, so whether primordial black holes can be all the dark matter in the universe, there are already a lot of upper limits in different mass ranges on their abundance, as you can see. And this is a field that is evolving very, very rapidly. And there are a number of constraints, for example, from lensing and other observables. There is an open window at very small masses that I will not cover today, but you may ask if you are interested, since there is some development here. And then there is a window at very high mass where there was a lot of development as well very recently. And that's what I will discuss now. So we are talking about black holes of tens or even possibly hundreds of solar masses. And the idea here of this series of papers that I want to present is whether we can observe these objects or constrain their presence by looking at the radiation, at the multi-wavelength radiation from radio waves all the way up to like X-rays that could be accreted onto them. So we know that the galaxy is a reservoir of interstellar gas. We know that if primordial black holes are a significant fraction of the dark matter, there would be really many objects like this in the solar mass range in the Milky Way. So in our galaxy, there could be even 10 to the 11 or more objects, or depending on the mass. And there is a lot of gas. So why don't we why not expecting radiation, for example, in the radio band and X-ray band, that are two bands that are typically considered when looking for accreting compact objects. So we studied this problem, and here the complicated piece of physics here is the physics of accretion. So how accretion on a compact object works. And over time, in different papers, we considered first a very basic textbook approach of accretion, which is very often considered in many works related to searches for compact objects, which is the Bondi-Hoyle-Littleton formula. So this is really fluid mechanics, Euler equation, continuity equation, and you get an accretion rate that scales with the square of the mass of the object and with the inverse cube of the speed of the object. So fast black holes accrete very inefficiently, heavy black holes and slow heavy black holes accrete very, very efficiently. And this is the first approach that one may think about, but it's interesting to consider more advanced approaches, in particular, the state of the art about accretion physics in the community that studies this effect is this set of numerical simulations embedded, and the results of this simulation are embedded in a semi-analytical parameterization, which takes into account the radiative feedback. So the fact that while matter is accreted onto black holes, a lot of ionizing photons are emitted because the gas is heated up by this process. And so you form a ionized region around the object. You form a shock in front of it. You form an ionization front and then another shock in front of it. So you form a complicated structure. And the accretion rate has a more complex behavior with respect to speed. In particular, it features at low velocity, it actually increases with speed. So that's the opposite behavior with respect to the Naive-Bondi formula. And at very high energy, at very high speed, you recover the trend given by the Bondi formula. And that's because the formation of this ionized region at very small speed, if you compute the jump conditions of the thermodynamic quantities in this ionization front, you find that the density within the ionization front actually increases with speed. So if you apply actually the Bondi formula to the region inside the ionized region, you get this behavior. So you get an increasing accretion rate with speed. So this is basically a state of the art that we have. And it's very nice to apply this physics, this formalism to an ensemble of moving black holes that wander around in our galaxy. So we basically implemented this formalism, and we asked ourselves whether we can constrain the abundance of black holes by comparing with data, with astronomical data. So the data that we have, in particular, we focused, I have to say, on the galactic center region. So that's a very interesting region for this kind of searches because the gas density is very high in there, and we have a complex of molecular clouds that is very massive, and so it's a good target for this kind of search. And also, if the black holes track the dark matter profile, you expect to have the peak in your primordial black hole distribution if they are a significant fraction of the dark matter. And then we have a lot of data there. We have a catalog of radio sources from the VLA experiment. And we have a catalog of hard X-ray sources as well from the NuSTAR satellite. So we have a number of sources in this region. And the idea is to understand whether the number of predicted sources, given the knowledge that we have of the accretion physics and the gas distribution and the black hole distribution, is larger than the number of observed ones. So we developed some Monte Carlo simulations for the emission of black holes in the inner galaxy. We took into account how gas is distributed in the inner galaxy, in particular in the galactic center. We predicted a number of bright X-ray and radio sources associated to the process of mass accretion. And we derived in these two papers two upper limits on the abundance of primordial black holes in this mass range. And the second one is stronger. You can see that only a per mil fraction of the dark matter is allowed to be in the form of primordial black holes. This one is stronger because we are using this state-of-the-art modeling of the accretion physics, which has a very different behavior and actually peaks. And actually, the accretion rate peaks at high speed. So the constraining power comes from a completely different region of the phase space of primordial black holes, a region which is more populated because you are not relying on the very low velocity tail for the constraining power as for the Bondi formula. So with a more realistic, if you want, model for accretion, we get this strong upper limit. But this is only the starting point, I think, because there are now we are keep working on this, and there are future developments that will be addressed very soon. So I mean, stay tuned, because the role of clustering, I think, has to be addressed, and also the impact of a complicated mass function. So we may wonder whether there is a possibility that only a subdominant population of black holes exists in this mass window, but actually if you consider a peaked multimodal mass function as the one that has been considered several times in the literature and is physically motivated, for example, by scenarios where some events in the early universe, like for example, a QCD phase transition or other events may are expected to alter the number of relativistic degrees of freedom, and therefore cause a pressure drop in the medium, soften the equation of state, and make it easier for black holes to collapse in the early universe. So you may expect to have peaks at different mass scales associated to events in the early universe, and these mass functions are now reconsidered a lot in the literature, and it is interesting to ask whether we can turn this bound into a window of discovery, for example, for the peak around 2030 solar masses associated to this broader context of a wide multi-peaked mass function. So this is something that we would like to address, and also we would like to address the prospects for future experiments, like for example SKA, in improving this bound or providing a detection. Let me also mention that with my student Francesca at EFT, Francesca Scarcella, we are studying also how this mechanism can be used to look for astrophysical isolated black holes. So yeah, I will just flash this. This is a very nice multidisciplinary connection. So we realize that in the astronomical community, isolated primordial black holes are really an interesting target. They were never observed. So we only observe black holes when they either merge by gravitational waves or where they accrete gas from a companion star. But we never observe isolated black holes that wander around the galaxy and just accrete gas from interstellar gas. And there should be a population of as many as 10 to the 8 of these objects in the galaxy. So we only see the tip of the iceberg by observing the ones that accrete from stars, but we don't see this huge amount of isolated astrophysical black holes that should be there, since they are the endpoint of stellar evolution. And so we are applying this formalism, the paper will be out very, very soon, to this population, and we are trying to assess the opportunity of SKA, of this new radio observatory that is going to be set up over the next decade, to the opportunity to detect a radio flux associated to these objects. And we are studying a parameter space associated to the properties, for example, of the interstellar medium, the number of black holes in the galaxy. And it seems that a very large number, so hundreds or thousands of astrophysical black holes, can be detected with this method, with future radio experiments. And this is very important also for the primordial black hole search, because it would be, if you want, a astrophysical floor to primordial searches. So by analogy with the direct detection experiments, for example. So we are looking for primordial black holes, but we have to deal with this unavoidable floor of 10 to the 8 astrophysical objects in the galaxy. So it's very important to also study this aspect. So the possibility to detect isolated astrophysical black holes. And you can see, for example, in the left-hand plot, the radio flux is a function of black hole speed, and the threshold given by SKA is the dashed horizontal line. You can see that over a wide range of velocities for reasonable values of densities of gas in the interstellar medium, you expect to have a reasonable radio flux above the threshold for detection for SKA. Okay, so that was the first part. So I think in the next 10 minutes, more or less, 10, 12 minutes, let me change a little bit the topic, and let me talk about another aspect, the dark dress part that I promised you at the beginning. So here, we want to ask a different question. So we want to so now we are agnostic on the nature of the dark matter. We are not asking ourselves if the dark matter is made of black holes, but since we believe, and now we have some evidence from LIGO that intermediate mass black holes exist, so we have a very we may have a very important population of black holes that are more with a mass larger than 100, 1000 solar masses, but that are less massive than the supermassive ones. Okay, we want to understand whether we can detect dark matter by studying the overdensities of dark matter that may form around these objects. So that's the other question that we are trying to address. And we expect, I mean, the overdensities of dark matter around these objects with the power law density profiles. Actually, we expect overdensities of dark matter around both primordial black holes and intermediate mass black holes. And we expect the dark matter to reach very high density in this around this object. So this can be studied with analytical treatment or with numerical simulation. Here you see a number of references if you're interested where this problem of the formation of this overdensity is studied. And typically, okay, if you think about an intermediate mass black hole in particular, the idea is that this intermediate mass black hole would be sitting probably at the center of a dark matter cusp. So, for example, in a cluster or in a small galaxy or in a globular cluster. I mean, there should be a pre-existing cusp of dark matter, and then the growth of the black hole would alter the distribution of dark matter around it, and turn the cusp into a spike. So we can have this spiky structure around the black hole with a power law density profile, and the dark matter can reach very large densities, like up to 26 orders of magnitude above the local mass density. So this density is very relevant and can impact. So the question is whether it can impact some observables associated to the black holes at the center of the structure. And in particular, we studied different ways in which the dark dress can influence the black hole, the phenomenology of black holes. But in particular, I will now focus on the impact on the gravitational wave that could be emitted by these black holes. So that's the system I would like to study, which is sketched here. So the idea is to consider these systems that are called intermediate mass ratio in spirals. These systems are a potential target for LISA. And they are composed by a central massive black hole and intermediate mass black hole that could be of any origin. It actually could be of astrophysical origin. It could originate from the direct collapse of a cloud, of a massive cloud of gas. It may originate from a population of 3 stars. I mean, it may have of course, it could be seeded by primordial black holes, but we don't need to assume that it is primordial. We just have to assume that this object exists as we start to see evidence. And then we consider an ordinary compact object like a neutron star or a light astrophysical black hole around few solar masses, for example, that orbits around the massive compact object. And so we have this very asymmetric system, and this system, if this system is embedded in a dark matter dress, in a strong overdensity of dark matter, you have 3 effects that govern the evolution of this system and the spiral of this system. So we have, of course, the gravitational pull. Then we have the back reaction from gravitational wave emission. So this is a typical system that emits gravitational waves, and the gravitational wave emission causes the system to decrease its orbital energy, and so it implies an in-spiral of the object, of the small object around the massive object, and then and the spiral is given by this back reaction from gravitational wave emission. And then you have dynamical friction caused by the dark matter dress, if the dark matter is present, which is due to the many slingshot effects that can that characterize the interaction between the compact object and the dark matter around around it. So this could imply a dephasing of the waveform. So the effect of gravitational friction may be visible in terms of the dephasing of the waveform, as studied already, as mentioned already in some papers. But what we did very recently, yes?
5 minutes left.
So, oh yeah, perfect. I have 4 or 5 slides left. So the main point of a work that we recently published, and actually it's the PRL part is still under review, is that if you do some energy balance of the system, so if you compare the energy that is lost due to that is transferred actually from the compact object to the dark matter dress due to dynamical friction, and if you compare this energy to the binding energy of the halo, you have this plot. You see that the binding energy is much less. So the energy transfer due to dynamical friction is much larger than by even 2 orders of magnitude than the binding energy of the halo. So this system has to be studied with a self-consistent model that takes into account the feedback on the halo itself. So that was the main finding, and we actually modeled in a self-consistent way both the spiral of the system and the evolution of the phase-space distribution of dark matter due to the energy injected in the system because of gravitational, because of dynamical friction. And this was done in a statistical way by assessing the probability for a particle that is in the dark matter halo to be upscattered by the gravitational interaction with the compact object and receive a certain kick. So we basically now, well, okay, this is a bit technical, but I will skip the details. I will we actually modeled the evolution of the phase-space distribution of the dark matter, thanks to a very actually quite simple semi-analytical prescription that we backed up with numerical simulations. And the main result is the one that I will show in the last 3 minutes. So first of all, we noticed. You can see this animation that while the compact object slowly spirals around the intermediate mass black hole, you can see on the x-axis the distance, and you can see the spike profile. And you can see that the spike profile is altered a lot during the spiral due to this feedback on the halo. So the effect of dynamical friction is really visible. So you can see that while the object in spirals around the intermediate mass black hole, you can see the particles, the dark matter particles, especially the slow ones, are upscattered and are transferred to other orbits. So the region close to the compact objects is actually depleted, and this ultimately gives rise to an anticipated merger. So we developed these spectrograms in which we have the frequency of the wave, of the emitted wave, on the y-axis, and then you have time on the x-axis. So you can see that with respect to a situation in which you don't consider the feedback, you have a very different prediction. So that would be the blue versus the red line, and you have maybe in this plot it's clear, you have an anticipated merger. So basically, if you consider the black line, which is the merger in vacuum, so with no dark matter at all, and then you consider a spectrogram associated to a static dark matter spike, you have an extremely anticipated merger, the blue line. But the blue line is actually not physical because we showed that the feedback on the dark matter dress is very important. So we predicted the spectrogram for an evolving dark matter spike with the feedback included, and we found the red line. So you see that the effect is smaller with respect to the one previously computed without taking into account the feedback on the spike, but still very relevant and observable. So this is a channel of detection for an overdensity of dark matter around an intermediate mass black hole with LISA. You expect to have days or weeks, a merger anticipated by days or even weeks with respect to the situation in vacuum. And this dephasing is actually very important to model, because the thing is that if you miss this modeling, if your waveform that you predict does not contain this dephasing and this anticipated merger due to friction, you may completely miss the observation, since there is this matched filtering technique in gravitational wave observation. So you have to know the template of your wave if you want to have a chance to detect it. So you may miss completely the detection of this very important type of system if you don't take into account this effect. And it is a channel of detection which is also very sensitive to the slope of the spike itself. So you can do physics with this. You can consider different hypotheses on the nature of the dark matter that produce different slopes of your spike, of the dark matter spike, and you have different prediction for the anticipated merger due to this effect for different cases. So yes, my conclusions, we have two different types of black holes that are typically of astrophysical origin. We may have a population of primordial black holes, and a promising avenue for detection of even a very subdominant population of primordial black holes in the mass range between 1 and 100 solar masses is accretion of baryonic matter onto these objects, and the subsequent emission of X-ray and radio photons. This is an interesting channel for detection. For now, we have an upper limit on the abundance of primordial black holes, but we may wonder whether a subdominant population can be detected in the future, also in the context of extended mass function. And then we showed that dark matter can accumulate around intermediate mass black holes and alter the gravitational wave emission from these objects, which is a science case for LISA and is a potential avenue for detection of dark matter around black holes. Yeah, that's all.
Thank you. Is there any questions or comments?
Hello.
Well,
I want to
hello.
ask a question. Well, actually, there are two. First of all, in the animation, I can see that you show an animation of the dark matter merger inside, and the particles get accumulated around this merging halo, merging black hole. So, is this a simulation or is it just a model?
Okay, yes, this is a numerical simulation. This is done with Gadget, actually. So basically, we implemented an n-body simulation with the compact objects and other compact objects around. And then the dark matter halo is modeled as the many pseudo-particles, right, that should capture the phase space distribution of the dark matter. And it's basically how the dynamical friction works. Actually, well, to be precise, okay, we use the numerical simulation to be precise. We use the numerical simulation to study how the friction effect works. But this plot was actually produced with the semi-analytical prescription inspired by numerical simulation. This is very important because in the n-body numerical simulation, we don't have the inspire, we don't have the gravitational wave emission. So this plot was actually done implementing the semi-analytical prescription for the evolution of the spike in a solver that takes into account the back reaction from the gravitational wave emission and so on. But this is backed up by numerical simulation.
I see. So the problem here you want to solve is just trying to see the effect of dynamical friction and
yes,
using the Newtonian approximation to solve all the things.
That's true.
Okay, the second question is actually a comment. So as long as there is a dark matter spike around such supermassive black hole, then supposedly there will already be baryonic matter, which will have even much higher density around the supermassive black hole. So when any smaller dark black hole merging into the large black hole, it has already collided with many baryonic matter. So that will also produce more EM waves. So supposedly there will be also a synergy between this EM wave and the gravitational wave, right?
Oh yes, absolutely. So first of all, yeah, let me comment again on what you said. So yes, we were Newtonian, but actually we plan to use some post-Newtonian correction, in particular when you are close to the innermost stable circular orbit, where they could be relevant. But most of the dephasing is accumulated at like 200 gravitational radii when the Newtonian approximation is fine. And then, yes, there could be baryonic matter in principle, depending on the formation mechanism of the black hole. Actually, we don't know. There might be. I mean, the more massive probably the black hole, the more you have a chance to have some baryonic matter. And yes, I agree that the impact of the interplay with baryon accretion has to be studied. And yes, there could be some chance to have multi-wavelength studies, because the baryonic matter could emit radiation. So yes, that's a good point. That's something to be studied.
Okay, so David, can you ask?
Hi, Daniele. So I have I don't know if it is a very silly question on the first part of your talk, where you were talking about the accretion models on black holes, and then you presented your updated results. And I had the impression that you're using a two-dimensional accretion model. Is this because there is no three-dimensional ones, or would someone expect something different if there were? Yeah.
Yeah, yes. This is well, this is already very advanced, but yes, that's true. That you have only two dimensions. Yes, you have this ellipsoid. But the geometry, yeah, absolutely. There's nothing more advanced than this actually. And but actually no, that's not true. Actually, there was an update of this paper in 2020 with some 3D simulations, if I'm not wrong. But this trend is, this trend is very solid. So the fact that you form this structure and you have an accretion rate that grows and then decreases. So actually, you don't want to study too many details. For this prediction, you are mainly interested in this trend. So the fact that the accretion rate increases with the black hole speed and then decreases. And I think this is very solid, and it can be shown also, with just pen and paper that this happened depending on the properties of the ionization fronts. So this is solid.
Okay, so Sven.
Thank you.
Yeah, I have a question also on the first part of your talk, when you were talking about the future prospects of extending the ranges or pressing the ranges down. How far in solar masses can you go down with your method? What do you think? You stopped at 20 or so far, right?
Yes. No. Okay. So this method, since there is this m-squared scaling of the accretion rate, you can't go too low. You can't go lower than 1 solar mass. So the idea is actually
already be great, no? To fill the gap between 1 and 20. So.
But the main peak of this multimodal mass function is really at the border of what you can probe. But you need complementary probes for this, and lensing is actually very important complementary probe. But still, it's since all the bounds have to be recomputed given given whatever mass function. So it's very important to recompute the bound and assess whether this bound is compatible with this mass function if the integral sums to 1. So this is already an exercise that has to be done. And then yes, I agree. The low mass part can't be probed with accretion, and it has to be probed with, for example, lensing. And there are hints actually from lensing, for example, the Ogle experiment observed some hints in the planet mass range, but they have to be confirmed, of course. This could be some astrophysical phenomenon, of course, but still, lensing is the complementary probe for low mass, I would say.
Okay, thanks.
Andrew, sorry for because of time, so I think that we have to finish this first talk. So
okay,
we can.
No worries. I'll message you.
So then, thank you again.
Thank you.
Okay, good. And the next speaker is Takahiro, right? Takahiro. So could you share your screen?
Yes. Do you see my screen?
Yeah, I can show.
Oh, okay. So, I will talk about this primordial black hole evaporation and also.
Sorry. So I show your full screen, the desktop screen, not slides.
Oh, I can't see what people are seeing. Do you see the desktop?
Yeah. So web page.
Web page. Okay. So stop sharing. Okay. How about this?
Yeah, I can show. I can see. So can you change the? Okay, it works. Okay.
Okay. Can I start?
Sure.
So, okay, so now the previous speaker talked about primordial black hole as well as astrophysical black hole. And I will talk about much smaller primordial black hole. And it is very small so that it evaporates before the Big Bang nucleosynthesis in the early universe. And also its connection to the gravitational waves. Okay, and so let me first mention that this observability of these gravitational waves is limited to some ideal case. But nevertheless, if some conditions are met, this can be detected in the future gravitational wave interferometers in the space, such as this IGO and BBO, LISA. So let's see. So do you see the change of the slide? Okay, so let me begin with some basic motivation to prove the universe using gravitational waves. And as you know, if you use electromagnetic waves, then there is the last scattering surface beyond which we cannot see directly, from which the cosmic microwave background comes from. And so in this context, gravitational waves are a useful probe to see the very early universe and hence the high energy physics. And this kind of Big Bang nucleosynthesis epoch, and also probably there was a period of inflation. These are relatively well established compared to this dark universe, the topic of the conference. So, however, there may be something like this. So this is just one example, but after inflation, maybe inflaton reheats the universe, or there may be some preheating. Anyway, there's radiation dominated era, and gravitational waves can probe this kind of very early universe. So let me mention some possible sources of gravitational waves. Of course, this depends on the physics models. For example, new physics models, what kind of models you consider. There may be, for example, cosmic strings or phase transitions, etc. I cannot review all of them, but one famous source is that inflation. I forgot to show this. So using the gravitational wave spectrum, we can probe the various features of the early universe. For example, we can probe we can see the spectral slope change of the gravitational wave, so that, for example, the reheating temperature can be probed. And also, we can also consider non-minimal scenario in which, for example, massive particles like moduli or gravitino, or even massive objects, not elementary particles like primordial black holes, may dominate the universe. So in that case, there is a matter-dominant epoch before the final radiation-dominated era. And these can also be probed. And also, this will become important later in my talk, whether the transition, this reheating transition, is gradual or sudden. And as I a little bit mentioned, there are various sources of gravitational waves, and the famous one is from the direct production of gravitational wave from inflation. So this is the primordial tensor perturbation, and this is bounded by the upper bounded by the value of the tensor to scalar ratio observation. And also inflation, as is well known, inflation also produces the primordial scalar type perturbation. It is nothing but the curvature or density perturbations. And this in contrast to the tensor mode, this scalar perturbations has been well already established, I mean, measured by CMB observations, and it's very small. But if we go to much smaller scales than the CMB scales, then this scalar perturbations may be larger or smaller. And suppose indeed it is enhanced by some mechanism. In such a situation, gravitational waves are actually emitted from enhanced curvature perturbations because scalar and tensor modes couple to each other beyond the linearized level. So this coupling is built in the general relativity. So if you consider second order of the cosmological perturbation theory, the gravitational waves are produced from scalar modes. So this will relevant in the later discussion. And I put some equations here, and you don't not have to see the details of the formula, but the point here is that schematically, the second order of perturbation, the gravitational wave, the tensor mode, is sourced from the first order contribution of scalar mode. Here, scalar mode is the scalar degree of freedom of the gravity, namely the Newton potential, gravitational potential, or equivalently the curvature perturbations. Okay, so this will become the main mechanism of the gravitational production. But let's move on to the primordial black holes. So this is already reviewed in the previous talk, but let's briefly go through. Depending on the mass of the primordial black hole, it can, for example, become dark matter candidate, or it can explain the abundance of binary black holes, which is relevant for the gravitational detection by LIGO and Virgo collaborations. So in this talk, we will consider much smaller, tiny primordial black holes whose weight is about 10 to the 4th, 3rd gram. So it's like animal or car or something like that. And there are also various production mechanisms produced in proposed in the literature. And so for concreteness, in this talk, I will consider the direct gravitational collapse of enhanced curvature perturbations seeded by inflation. So this is, in a sense, collapse of the universe itself into the primordial black hole. And after the production, there are several processes that change the mass of the primordial black hole, astrophysically or quantum mechanically. And in this talk, I will focus on this quantum mechanical process, namely the Hawking radiation. And I do not show detailed formula, but this is a very short and useful formula saying that the lifetime of the black hole is proportional to cubic of its mass. And when its mass is about 10 to the 15th gram, its lifetime is comparable to the age of the universe. Okay, so although we consider very light PDH, I just show this compilation of observational constraints. This similar figure is shown in the previous talk. And if we consider lighter PDHs, then even if it has already evaporated from the current universe, there is still constraints from, for example, Big Bang nuclear synthesis and cosmic microwave background observations. And if we consider much lighter PDHs, this is the full compilation of the existing observational constraints taken from this review. But, so for very light PDHs, about 10 to 5th gram, for example, there are some constraints named Planck or LSP. But in my opinion, some of these constraints are at least model dependent and not so robust. For example, I like supersymmetry, but nowadays we do not know at which scale SUSY lies. So this LSP constraint, LSP overproduction, is not so reliable. And also, that this Planck means that Planck mass relic constraint. So this assumes the Planck mass relic after the Hawking evaporation. And I think most string theorists do not believe this seemingly non-unitary processes. So in my opinion, it's like more or less like this situation. So, and in our work, we find some prospective constraints with some assumptions from null detection of gravitational waves via the, by the future gravitational waves like DSIG or LISA. So this SIGW denotes scalar-induced gravitational wave, which I mentioned in the introduction. And this black dotted line, this denotes the line above which PBHs dominate our universe, the energy density of the universe. The vertical axis shows the initial abundance of the primordial black hole. Energy density of the primordial black hole divided by the total energy density when PBH is formed. So this has also the interpretation of primordial black hole formation probability in a given Hubble patch. Okay, and the horizontal axis is the mass of the PBH in gram unit or solar mass unit. So this is the context of our work, and let's discuss the more details or mechanisms of the gravitational wave production. So if you consider above this dotted line, the scenario is automatically like PBH dominating scenario. So let's consider this in more detail. Suppose that PBH is produced in a radiation dominated era. And then because this energy density scaling is non-relativistic, so at some point it will dominate the energy density of the universe. And after that, PBH will evaporate, it completes its evaporation. So after that, the reheating temperature is typically 30 TeV for this 10 to the 4th gram PBH. This is the initial mass divided at the formation. And this domination happens if the initial abundance is sufficiently large, larger than some critical value given by the ratio of this temperature. And there is another temperature in this problem, namely the Hawking temperature. And each PBH has this temperature, like such as 10 to the 9th GeV or so. And let me briefly review various gravitational wave production sources in this scenario, because it's interesting to see that there are several sources. So these are just a schematic figure representing these three epochs. At the PBH formation time, so PBHs are supposed to form from enhanced scalar curvature perturbations depicted in this figure. And not only PBHs, also gravitational waves are produced from these enhanced curvature perturbations. So from this, scalar-induced gravitational waves are produced. Second, by the time of this PBH domination, some PBHs will find a partner and form a binary. And as is well known in recently, these merger events produce gravitational waves. And so this is the second source. And third, there's also gravitons emitted from Hawking radiation, and this also constitute the stochastic background of gravitational waves. Last but not least, there's density perturbations growing during this matter-dominated era, namely the PBH-dominated era. And then this fluctuation is converted to the density perturbations of the thermal bath. The thermal bath is created by this decay, namely the evaporation of PBHs. And interestingly, this fluctuation oscillates quickly compared to the Hubble time at the reheating. And this dominantly resonant via the resonant processes produce the scalar-induced gravitational waves. So this is the, again, scalar-induced gravitational waves, but produced at longer scale compared to this SIGWs at the formation scale. So in this way, there are at least 4 channels of gravitational wave production in this scenario, in a single scenario. And as you see from this figure, this last component could be, only this could be proved by the future observations like the SIGO or BBO. So let's consider this. And I will explain a little bit more detail about this growth of density perturbations during this PBH-dominated era. The growth of density perturbations is well known, written in the textbook of the cosmology. So this is very standard phenomena. And this growth is proportional to the scale factor of the universe. And this situation, via the Einstein equation, corresponds to the non-decaying gravitational potential, even inside the Hubble horizon. And this situation makes the source term of the second-order tensor equation motion constant. So you can easily see that there is a constant solution of the tensor mode. And so this can become the propagating gravitational waves after this matter domination is converted to the radiation-dominated universe. But there is a non-trivial point here because so this constant is something like potential energy of gravitational waves, but this is not yet propagating freely propagating gravitational waves. So the efficiency of this conversion significantly depends on this transition speed, the reheating transition speed, namely the adiabaticity of this transition. In a previous work, we found that if we compare the conventional exponentially decaying case and the ideal really sudden transition case, then the final gravitational wave strength differs from each other by tens of orders of magnitude. So this really matters. And interestingly, the PBH evaporation, the last stage of PBH evaporation is very explosive, accelerating phenomena, self-accelerating phenomena. It's unstable towards the end of its evaporation. So if we define the decay rate through this formula, namely this decay corresponds to the evaporation of PBH, then decay rate diverges towards this completion of evaporation. And of course, divergence is regulated by some quantum gravity effect at least, but up to that, this divergence is really a physical effect. So in this sense, PBH evaporation is more sudden compared to the standard exponential decay of, for example, moduli or inflaton. And then these enhanced density perturbations are quickly or efficiently converted to the density perturbations, or in physical terms, sound waves in thermal bath. And this corresponds to the fast oscillations of the gravitational potential. And then this resonantly produced the second order gravitational wave, the scalar-induced gravitational waves. And so this process, this production process mechanism is due to these sound waves and oscillations in the thermal bath. And this thermal bath is created by the PBHs, but PBHs are no longer there. And it's like they are already gone and dead. So in this sense, we named this mechanism as poltergeist mechanism, because it's like as if ghosts of PBHs make merry in the thermal bath and sing a song and oscillate the thermal bath, and then gravitational waves are produced. Right. And the technical details are somewhat long, so I did not explain all the details, but I will pick up some key points. So as I explained, this adiabaticity is crucially important. So any factors which may smear the transition timescale may affect the final strength of the gravitational waves in this mechanism. So we have to assess such kind of possibilities. So these scalar perturbations are, because these are sources of the tensor mode, so we have to consider these scalar perturbations. And the horizontal axis is the conformal time, and the vertical axis is denotes various quantities. But please look at these greenish lines. This denotes the gravitational potential or the curvature perturbations. And you see that there are some suppression after it enters to the PBH-dominated era, this line. And there is some suppression due to the residual radiation in a matter-dominated universe. And this is a standard effect. It's also written in some textbooks. So instead, we focus on this suppression due to the pH evaporation. And this is interestingly, during matter domination, the matter fluctuation grows compared to the radiation fluctuation. So even if at the moment of reheating, where the radiation energy density and matter energy density is comparable or equivalent, equal to each other, their fluctuation ratio is different. Matter is larger. That's why this gravitational potential is dominantly determined by the pH fluctuation. That's why this pH fluctuation decays like pH itself. So this decays quickly just before the completion of the evaporation. That's why there is a rapid decreasing in this just before the evaporation. And after it becomes radiation domination, there is a quick oscillation. This is the standard behavior in the radiation-dominated universe. So we have to, so we normalize this phi 1. The initial value is normalized as 1. And you see from this figure that this phi becomes 0.5 or 0.1 in this figure after the evaporation, just after the evaporation. And this, so this suppression factor is important, and we quantitatively assessed this kind of evaluated this suppression factor. Another factor is that finite mass width. So in a simple study, in the literature, people consider, for example, monochromatic mass, single mass. This corresponds to delta function distribution. But if you consider more realistic cases, there would be some mass width. And because the black hole lifetime is proportional to the mass cubic, this distribution in mass corresponds to distribution of lifetime. That's why this may affect the time scale of the reheating transition. And indeed, it significantly affects the result. And this figure shows that, so we consider log normal distribution, and this figure shows that as we increase the width of this Gaussian, then this suppression factor, I mean, this value, suppressed amplitude, exponentially decreases. So this is a drawback of our mechanism, namely, so this enhancement of gravitational waves are only effective when the width of the mass distribution is very narrow. And this is the result of our calculation. The horizontal axis is the wave number or the frequency of the gravitational waves, and the vertical axis is the strength of the gravitational waves. And this, I'm assuming you see mouse cursor. This line corresponds to the vanilla scenario second order gravitational waves extrapolated from the CMB scale. And because the CMB scale, the scale of perturbation is very small, 10 to the -9. So correspondingly, this gravitational wave strength is very weak. However, due to this pH domination and the evaporation effect, the gravitational wave strength is significantly enhanced. But this is in the case of a monochromatic case, the thick black line. If we consider small but finite mass distribution, then this decreases several orders of magnitude. These are denoted by thin black lines. And of course, if the initial pH mass change, if initial pH mass vary, then the lifetime changes. So this time scale in the universe when this evaporation happens also changes. That's why this scale depends on the initial mass of the pH. Okay, so, and you can see here that for around 10 to the 4th gram pHs, these gravitational waves may be detected by BBO or DCIO. And these figure shows the lines corresponding to signal to noise ratio 1 unity. the horizontal axis is the initial PBH mass. Vertical axis corresponds to the initial fraction abundance of the primordial black holes.
So 5 minutes left.
Thank you. This solid line corresponds to this LIGO, and dashed line only in the right panel is LISA. The left panel corresponds to 1 year observation, and the right panel corresponds to 10-year observation. So you see, so the relevant mass range is about 10 to 3rd to 10 to 5th gram, and the abundance which might be probed is about above 10 to minus 7th or so. And we can also analytically derive this characteristic scaling. This mainly comes from that this constraint is on the duration of the matter-dominant era, which is proportional to beta over beta minimum. And that's why the constraint of beta is proportional to beta minimum, and evaluated like this. So let me summarize. Gravitational waves are induced from the curvature perturbations right after the PBH evaporation in the PBH dominated scenario. I reviewed also other gravitational wave sources which may be emitted during the evaporation or at the formation time. But the key topic I discussed in this talk is produced just after the evaporation. So this is a new interesting point. And this we name this as the poltergeist mechanism, because it's like poltergeist. And the resultant gravitational waves can be so strong that the future gravitational wave observatory, space-based interferometer, this LIGO, PBO, or LISA may detect them. But only if the PBH mass function is narrow. So this depends on, so you have to consider some model or mechanism to produce such mass distributions. And so, however, if you have some new physics models not necessarily related to PBHs, for example, if you have some very quick first order phase transition which triggers the matter dominated era to radiation dominated era, then such a process may trigger the poltergeist mechanism. Gravitational waves may be observed. But again, the time scale is very important, so you have to examine that point. And in terms of PBH constraints, although this constraint depends on the mass distribution width, the previous constraints also are based on some model dependent or not so robust assumptions. And of course, it's so difficult to constrain the physics occurred much before the Big Bang nucleosynthesis. So this is at least an qualitatively new and independent prospective constraints for the formation probability of the PBHs. Thank you for your attention.
Thank you. So any questions or comments? So, yeah, then I have one questions about the gravitational. So you mentioned some gravitational protection from some direct Hawking radiation.
Yes.
Yeah, so naively, maybe classically, I can think the gravitational wave is produced from some quadruple moment. So is there any such a I mean, so if I consider the Hawking radiation of the Schwarzschild black hole, then there is no quadruple moment. So is there some relation, or?
I think you can produce the pair-produced gravitons, and one negative energy graviton is absorbed by primordial black hole. So the spin is back reacted in the primordial black hole. So I think if there is spin angular momentum in the outside, then PBH will slightly rotate. But this is stochastically phenomenon. So on average, it's 0.
Okay. Good. So other questions?
Can I also ask a question?
Yeah.
You were mentioning, or you were saying that it could be detected only if the mass function is very peaked.
Yeah.
First of all, it didn't look that peaked to me, but okay, this is what is the prediction, or what do you normally expect there? Is there a model that would say, yeah, we should get something broader and therefore it would be very difficult to detect? Or what do the different theories about the evolution or the creation of PBHs say there?
I'm not sure whether I understand your question correctly, but
if you expect primordial black holes there, yeah, what do you expect? You say you could see them if the mass function is very peaked, but you said, we would need a model that predicts this. Well, so what do you expect normally? What do
normally
models that people are considering predicting there?
For example, if you consider the inflation model to produce primordial black holes, then some feature is assumed on the inflaton potential, any kind of feature, for example, very flat feature. Then some phenomena happen there, and typically any kind of such phenomena naively or a priori happens in a Hubble time in that epoch. So if you translate this into the wave number scale, then it is about order 1 in the log plot. One scale. But here we need not 1, but 0.01 in the dimension.
Okay.
So some trick is needed. For example, you need two time scales, some hierarchy, or some narrow resonance phenomena or something like that.
Okay, so but with the normal mechanisms, you would say this would predict such a broad spectrum that it would be very difficult to detect it.
Yeah, because these gravitational waves are not produced directly from a single black hole, but from the perturbation of cosmic fluid as a cosmic fluid. So that's why if there are many wide distribution mass, then this reheating transition time scale is smeared. So everything happens gradually and no violent phenomena happens.
Okay, thanks a lot.
Okay, so then let's finish the second talk. Let's thanks Takahiro again.
Thank you for attention.
And yeah, the third speaker is Jong-Pyong Hong from IBS CTPU.
Thank you.
So are you ready?
Oh, yes.
Right. So can you share your screen?
Oh, can you see the screen?
No. So yeah, the desktop.
Okay. Can you see it? Now? Now?
Right, I can see you. Okay, so start.
Okay. Thank you for the invitation. And I'm Jong-Pyong Hong in IBS CTPU, and I'm going to talk about new dark matter scenario where the lumps of fermion called Fermi ball generated after a first order phase transition can be the dark matter candidate of the present universe. And this work is collaborated with Sung-Woon Jung and Kepang Xie in SNU. So let me start. So as we know, the cosmological observations show that 27% of the total energy of the present universe consists of the non-baryonic matter, and new weakly interacting massive particles has been a popular explanation for dark matter for decades. And however, the continuously reported no results from the various detections drive us to consider some new dark matter scenario. And recently, actually, there have been a growing number of studies on the dark matter associated with the first order phase transition, where the difference in scalar wave during the phase transition may lead to non-trivial dark matter physics, for instance, non-thermal dark matter production, PBH production, and so on. And especially interesting idea is to trap the particles, some certain species, into the false vacuum bubbles, making the false vacuum not disappear completely and form some compact lumps contributing to the dark matter. For example, trapping the scalar particles into the false vacuum to form the Q-ball dark matter, a well-known compact dark matter candidate. And in here, we try to trap dark fermions into the false vacuum to form another type of compact dark matter candidates called Fermi balls. And yes, and the fact that the trapped particles are fermions, not the bosons, lead to different properties compared to the more usually considered Q-ball case. For instance, the Fermi ball is more excited energetically due to the Pauli exclusion principle, where the fermions occupy the higher energy states, since it cannot condense in the ground state only, just like the scalar in Q-ball case. So as a result, the Fermi ball typically has heavier mass for a given charge compared to the Q-ball case. And we will see that this difference in detail later. And the mechanism of the compact dark matter formation after the phase transition is illustrated in this figure, which in our case will be the Fermi balls. And the time order is, of course, A to D. And first, the true vacuum bubbles, the blue ones, nucleate in the false vacuum background, and which is the hot white one, and expand throughout the universe. And eventually, the true vacuum dominates, but the net charge after the annihilation in the false vacuum remnant actually is trapped into the bubble, cannot escape, and that pressure keeps the finite size of the remnants, competing with the shrinking pressure, and that makes the false vacuum remnant compact dark matter candidate. And this Fermi ball dark matter scenario requires the following three conditions to be satisfied, which also holds for the other compact dark matter after the phase transition. And then the first one is that the fermions should carry conserved charge, ensuring the stability of the Fermi ball relays. And we need some large mass gap of fermions between the false and true vacuum, so that they can be kinematically trapped in the false one. And we need conserved charge, but we also need some initial excess of the charge that should be somehow generated in the universe, since only the net charge survives from the annihilation. Okay, and here is the contents of the talk today, where I plan to trace the history to the Fermi ball formation from the phase transition, and review the individual properties of the resultant objects, the Fermi balls, and examine finally if they can contribute to the dark matter in the present universe. And finally, I will summarize the talk. And first, I will briefly give the basic setup, satisfying especially the three necessary conditions for the Fermi ball dark matter. And first, that we consider the global U1 theory of the dark Dirac fermion chi, which has a charge +1, and coupled to the real scalar phi through the Yukawa coupling. And this U1 symmetry will guarantee, as I mentioned, the stability of the Fermi ball relics. And also, if we use the gauge U1 symmetry, actually the Fermi balls become unstable due to the Coulomb repulsion, because we also need some gauge field configuration. So here in this work, we work with the global symmetry. And I also mentioned we need some mass gap between the false and true vacuum. And the Fermi mass in the true vacuum, which comes from the Yukawa, should be larger than the temperature, actually, in order to be trapped into the false vacuum kinematically. And yeah, here is the condition. And this can be realized by either large BEV over temperature, which becomes a supercooling, or the strong Yukawa coupling. And we will actually see later that the supercooling with the order 1 Yukawa is good enough for the Fermi ball dark matter scenarios. Okay. And this is about the third condition I mentioned. I pointed out the U1 symmetry should be broken at some high energy scale in order to generate initial symmetry in the early universe. And this will give the net charge of the Fermi balls in the final stage after the annihilation. And here, actually, we can generate some concrete example. For example, similar to the leptogenesis thermally, and actually it is presented in the appendix of the paper. But in the main part of this work, we will just parameterize the symmetry, using the C-chi free parameter. Yes, somehow naively assuming that it is related to the baryon symmetry of the observed universe. And actually, finally, we will find the not that small compared to the baryon symmetry in our model can satisfy the dark matter abundance, etc. Yeah, we will see the detail later. Okay. And now we would like to get some picture of the thermal history from the phase transition to the Fermi ball formation, especially by defining some characteristic temperatures. And we know that the phase transition is the vacuum decay first order between two local minima of the scalar potential. and the critical temperature, which we call TC, is where the potential minima to potential minima become degenerate. Yeah. Which is of course separated by a barrier. And as the temperature falls below the TC, the universe starts to decay into the new minimum. Yes, which we will call scalar wave W, and this will become the true vacuum. And that vacuum decay probability in Hubble volume and the Hubble time, which is order 1, the bubble nucleation becomes efficient. And that is the definition of the nucleation temperature, Tn. And the decay rate, gamma, is written in this form, which we will use later. Okay. And next, we can also define the temperature called percolation temperature, where the true vacuum bubbles becomes first expand and becomes infinitely connected. And this is numerically determined in this work, where the PT is the fraction of the volume that remains in the old phase. And using that fact, we can also define the Fermi ball formation temperature, T star, which is where the false vacuum bubbles stop being infinitely connected. And it is called Fermi ball formation temperature because if it is not connected anymore, each remnant can shrink into a tiny size, and that can become the Fermi ball. Fermi ball release. And next, we specify the model a little bit by considering this kind of potential. We use the cubic term because we're considering the real color, and this generates local minima aside from the origin. And yes, and C denotes the thermal mass correction from the degrees of freedom, including pi itself. And we assume the other thermal corrections are assumed to be small. Then we drop the details, but the critical temperature and also the other temperatures are written by the set of parameters as a functions of C, mu3, and m phi, which is the mass of phi at the true vacuum, and the wave W0. Yes. So we can see that the critical temperature and the nucleation temperature is written by the parameters I mentioned. And the percolation and formation temperature is determined by the condition of PT. And the PT was the volume fraction of the old phase. And that is determined by the nucleation rate, gamma, and the expanding speed of the bubble warp, VB, which we will treat as a free parameter. So we have to decide its actual value later. So, and the next step is we determine these parameters and just use this one. One parameter to scan and plot the temperature, for as an example. And first, we will see later that to satisfy the dark matter abundance, we can set this U0 is of the scale of 100 GeV, and C chi is, as I mentioned, 10 to the minus second, not that small compared to the baryona symmetry. And this 100 GeV scale will also yield the gravitational wave signals at the millihertz, which will be relevant to the future space-based mission. And yes. And based on this fact, we can choose the benchmark values for parameters that I mentioned in our toy model. Basically, they're all in the same weak scale, but we just give some values for W0 and phi and the order of parameters, etc. Just leaving the mu3. Leaving the mu3. And we scanned the mu3 and to plot the 4 temperatures for characterizing temperature. And this becomes the plot. And as I mentioned, it also depends on the VB, the wall velocity, and we are setting this as the 0.6 that I should mention in this point. And okay, this will be the parameter range we will consider for the dark matter abundance, etc. And we can see that W over T is quite large. And this means we are in the situation of supercooling, and yes, and although Nicola is sufficient for the efficient trapping, as I commented previously. Okay. And okay, that was the example of the characterizing temperature of the phase transition. And I also mentioned that at T star, false vacuum bubbles start to shrink since the bubble are not connected anymore. And the maximal size of the remnant that becomes Fermi ball actually is determined by the condition that the bubble can shrink to the Fermi ball size before another true vacuum bubble is created inside. And that becomes the condition on the nucleation rate, gamma. And that determines R star. And that gives the typical size of a false vacuum remnant. And that in turn gives a typical charge that is trapped in that size. Yes. And that gives this formula, and FB is number density of the remnant here, and the F chi trap is the number fraction of chi trapped in the false vacuum. And this, I also assume that this is almost 1. I mean that the trapping is efficient, but I need to show some example that is quite right. And trapping fraction F chi trap is a function of the mass over temperature, of course, and repeat the wall velocity, because if yes, the wall velocity affects the penetration rate of the particle. And we can see that for a reasonably large m over t and relativistic v, p, the tripping is quite efficient, and quite generally with the fraction close to the 100%. And next, for a given m over t, the fraction f decreases with Vb because chi in the wall frame, because yeah, actually wall is moving, but in the wall frame, the chi looks like moving more energetically, having the higher chance to penetrate the barrier. Yeah, that was the description of the trapping fraction. And after we get after the shrinking, and we get the, after we get the typical charge, the remnant becomes the Fermi ball, and we need to determine the final size of the Fermi ball, because I mentioned that the trapped particles will give the pressure against the shrinking, and they will keep the finite size of the remnant, becoming the Fermi ball. And the first, we consider the energy of the remnant, which consists of the Fermi gas pressure inside, which will be the first term, and we get the surface, the energy term from the surface tension of the bubble, and of course the volume term, which comes from the energy difference, potential difference.
So
5
minutes.
Okay. And the surface term actually is neglected due to the large R in our case, and quite generally. And the mass and the size and Fermi ball are determined by energy minimization as a function of Q and U0. And actually we vary R to give to minimize the energy, and the result is that the mass is proportional to Q, and R size is proportional to the Q to the 1/3. And this is the basic properties of the Fermi balls. And actually we can see here that the Fermi ball is typically heavier and larger than the Q ball for a given charge, as I mentioned in the introduction. If we also look at the Q ball formula like this, the power is larger compared to this one. And this actually comes from the pressure term of the pressure term difference compared to the Q ball, because the Q power in the pressure term is different, like this. Okay. And here, if we consider our toy model and the benchmark parameters, we can estimate the typical values of the properties of the Fermi balls. And here we can see that they are very dense and sparsely distributed objects. And finally, we can discuss on the stability of the individual objects. And the first one implies that the chi has a smaller energy inside the Fermi ball than outside. And this gives the relation on the two scale U0 and W0. But we will consider similar scales, and order 1 Yukawa will naturally satisfy this condition. And the second one implies that the chi's energy inside the ball becomes smaller or larger total charge. So energetically favoring the larger ball for a given total charge, not splitting into the smaller ones. So it means the Fermi balls are stable against the fission into the smaller ball. And this is automatically satisfied from the linear dependence on the charge of the mass. Next. And here we can, since we studied the individual properties of the object. I mean, then we can examine if they can contribute to the dark matter abundance of the present universe. And if we use the formulas for the number density and the permeable mass, we can estimate the dark matter abundance from the Fermi ball like this. And here we can, of course, more accurately, we have to estimate the trapping fraction as a function of mass, temperature, etc. But if the trapping is efficient, we can see that the Fermi balls can explain the full dark matter abundance for C chi equals 10 to the minus second, and the U0 of 100 G. And yes, as I just mentioned, there could be some additional contribution from the chi outside if they, okay, first, even if the trapping is efficient, the chi can be thermally generated from other mechanisms. Yeah, and this gives the normal freeze-out formula like this. And if the trapping is not that efficient, then the chi escaped from the fault vacuum can be dominant, and the formula just becomes the contribution from the homogeneous chi plasma, whose charge is partially trapped in the Fermi ball, so decreased by the 1 minus f. And so we know all the contribution from our new dark fermion, and we set actually the total abundance from the fermion to the observed value of the dark matter. And from this figure, Fermi balls can explain full abundance. I don't think we can see this fact from the figure, but actually the C chi is chosen as the 10 to the minus second, as I mentioned, and generally the Fermi ball fraction is high. In the parameter region we're considering the 80 to the 90%. And we are also plotting the F chi trap, the trapping fraction, and we can see they increase together because the escaping contribution becomes smaller as the F increase. And we can see that it increases with the G chi, the Yukawa, because it suppresses the thermal contribution through the efficient annihilation. Okay. And we consider the other detections, but okay. As you can see from this content, what I would like to say is that it is unlikely that the Fermi ball itself produces the detectable signal because the number density of the Fermi ball is extremely small. So it is highly unlikely to be observed in any direct detection experiment. And although it is very dense object, but this is not that dense compared to the astrophysical scale, for example. So actually there are gravitational effects, or the event with the astrophysical objects will, those effects are expected to be weak. So as a result, we investigate another detectable gravitational wave signal from the phase transition. The phase transition, yes, it is just indirectly related to the Fermi ball dark matter, because Fermi ball dark matter also depends on the Yukawa coupling. But anyway, it is indirectly related. So,
Jongpyeong,
okay.
could you speed up a little bit?
Okay. This is almost the final slide, and yes, as a result, the gravitational waves can be is possible at the millihertz frequency if we consider the weak scale phase transition, as I mentioned. And this is relevant to the next generation gravitational wave detectors. Okay, but although it is gravitational wave and frame ball dark matter is indirectly related, gravitational wave detection does not necessarily imply a frame ball dark matter scenario, because as I mentioned, there is another parameter you call coupling. So it does not necessarily overlap with the parameter region for the pyramidal dark matter. So as a result, those two events are not that strongly connected causally. Yeah, that is actually the conclusion. So yes, here's the summary. Thank you.
And
oh yeah. I conclude that the scenario Fermi ball dark matter is possible, but indirectly related phase transition can give the gravitational wave signal. But these two scenarios is not directly related, but it can be worth considering. Yeah, that's the conclusion.
okay, thank you for your time. So, some questions about Chongpyeong's talk?
May I
Okay.
ask a question?
Yeah.
Because this is from dark word to Swampland, so let me ask this. So the U1 global symmetry may be slightly broken. So then I guess that there may be some annihilation signal or something like that. The Fermi ball becomes unstable, right?
Eventually?
Eventually, yeah.
No, eventually that kind of broken effect is negligible at the low energy. That's what we expect.
I see.
Yeah. So yeah, that's the reason it is hard to detect by any signal, I think.
Even if U1 is broken.
Even if, yeah, I think it is. Okay, that depends on which model what we are considering, but at least the breaking model we are considering at the appendix, for example, it is only effective in the high energy scale and completely negligible after the phase transition. But if it is possible, it will be interesting as well. If you can give some detectable signal by that interaction of
yeah.
Okay, so if there is no more question, then let's thank Chongpyeong again. Yeah, because my some wrong time management, so I think we already
I'm sorry.
minutes. Yeah, but I think yeah but I think it is good still take a 10 minutes break. So after 10 minutes, so we'll start 5:40 in Korean time and 10:40, right? In Madrid time. Okay, so thank you. Take a rest.
So then let's start. Hello everyone. So welcome to the second session of the morning, still devoted to cosmology. So we will have 2 talks, half an hour each. The first one will be by Luca. Maybe Luca, you can already start sharing your screen, and he will be talking about compact objects, and in particular, I guess also you'll be talking about axioms, probably something related to that. So please, Luca, go ahead as soon as you're ready.
Sure. So, okay. Great. Thanks a lot for the introduction. My name is Luca Visinelli. I'm currently a postdoc at Grappa, University of Amsterdam. Today I'll talk about recent and future developments on compact objects and dark matter in relation to light bosons, such as axions. So we already know that the standard model doesn't really provide particles that can be dark matter candidates, along with the other cracks that are present. For example, we don't have a neutrino mass, we don't have a quantum theory of gravity. We also don't have a dark energy candidate. We have little clues about baryogenesis, etc. That's why a vast array of ideas is currently being explored by the community. Just heard about balls made of fermions, but I would work instead of bosons in this talk, particularly on weakly interacting scalar particles, or WISP, like bosons, of which the QCD axion-like particle, or fuzzy dark matter are comprised. So the idea originally came from the 70s, when the QCD axion theory was formulated. The QCD axion represents sort of the archetype of the WISP. In brief, the QCD axion is related to the solution proposed by Bechet-Quinn of the strong speed problem that is plaguing the QCD sector of the standard model. On top of that, it was independently realized by Weinberg and Wilczek that the theory comes along with a new particle, which is called the axion, which in this Lagrangian is this A field that couples to the gluon field G mu, and also comes along with a new energy scaled, which is called the axion energy scale, and it's inversely proportional to the axion mass. How come a particle like a boson can be the dark matter, even if it's an extremely light particle? This is because it's produced non-thermally. So we consider the equation of motion of a light scalar in the early universe. We have the acceleration term, a friction term due to the Hubble expansion rate, and a massive term due to the potential in which the particle rolls. This is an equation which is valid only for superhorizon modes and for a quadratic potential, but it captures the essential ideas of the theory. So there's a transition that happens when the mass of the particle is of the order of the Hubble rate, at a time that I indicate here as the oscillation. Earlier, before this time, the boson behaves as a dark energy fluid, because we can neglect the mass term, because the Hubble friction is sufficient for the dynamics to be so that the energy density is approximately constant. When this condition is met, and here in this graph, this is represented by T over T oscillation over 1, the axion field starts to, or the boson field starts to oscillate coherently, have an energy else as the inverse Hubble volume. We see dark matter behaving. The energy density of an axion is then stored in the coherent oscillation of its classical field. This can also be used in laboratory research that directly look for the conversion of WISPs, of light bosons, into photons through WISP photon coupling. So we can assume that this particle has a 3-level coupling with fermion, either standard model fermions or hypothetical new fermions, which also couple to light. So this anomalous diagram create an effective photon wisp coupling, which is exploited in laboratories such as ADMX. And they act as a direct detection experiment, so an analogy of what's used, for example, in xenon. Whereas instead of a nucleus over which WIMPs recoil, we have a magnetic field over which the wisp converts into a signal. For Axiom, the signal is in the gigahertz, since we expect the axion to have a mass of the order of the tenths of a microelectron volt, if it is the dark matter. And the broadening goes with the velocity square, so we expect it to be in the kilohertz, since we expect this particle to be virialized with a velocity of order 10 to the minus 3c. So this gives rise to a falsifiable theory, because we basically can look for this particle in, for example, in resonators, as I discussed. Given the axion-photon coupling, in which the axion-photon coupling appears here, multiplying the axion field, the photon field, and its dual, we can look for, we can basically scan the parameter space, the axion-photon coupling versus the mass of the light boson of the axion. And we see that in the solid regions that have been already looked and excluded, whereas hashed region or more transparent regions are regions where the search will be undergoing in the future. The yellow band here represents different axiom models, different QCD axioms. So these are axioms that also solve the strong CP problem. If you step away from these lines, from this yellow band, you enter into the axion-like particle region, where you don't necessarily have QCD axioms. You have other axion-like particles that don't solve the strong CP problem, but they could exist. They could even explain the dark matter in the universe. Okay, this is my former student in Stockholm, Sani Vagnozzi, with whom we looked at the effect of string axions and axion-like particles in general. These are the probability in some units that we actually, with the posterior probability that we observe axions with a given mass over a given decade, and the possibility to detect them through some experiments in different bands. So we see that through different experiments, we cover a vast array of decades in mass, assuming that we either have an axiom that comes out of a string theory, which is the solid line, which means that we take the prior of our search to be related to string theory. So we, for example, we don't know where the soft supersymmetry breaking scale is, but we vary it between the electroweak and the Planck scale. Whereas for the dashed line, we let this constraint off, and we just consider axion-like particles to be present in the universe, and this is why this posterior probability is broader, and it's not as sharp as for the string axiom, for which we have more constraints. We see that basically for different mass decades, the axion-like particle serves different purposes. So if the mass of the axion-like particle is of the order of h0, the Hubble rate today, this could be the dark energy because of what I showed earlier. The field is yet to be set in motion because this condition m over h0 has not yet been fulfilled, or just got fulfilled today. If you raise the mass of your WISP, you get different effects that you can exploit, so that you can look for them. For example, if the mass is of the order of 10 to the minus 27 and 10 to the minus 25, you would see a cutoff in the cold dark matter power spectrum. If the mass is of the order of 10 to the minus 22 electron volt, what's known as the ultra-right axion, this would affect the galactic cores. And if the mass of the axion is of the order of 10 to the minus 15 electron volt, then the wavelength, Compton wavelength, is comparable to the size of stellar black holes, and this gives rise to the so-called black hole superradiance phenomenon. So this could be seen by the slowdown of spinning black holes. WISP, or axions of mass of order of 10 microelectron volt, are possible dark matter candidates for the QCD axion and are currently searched in the laboratory. Axions also make up compact objects. This is because the initial condition for the equation of motion that I showed can take different values in different patches of the universe. So it could be that in some patches, the initial condition leads to spikes in the energy density. So in this picture, we have a x and y axis, which represent the spatial coordinates of a simulation box, while the z-axis is the absolute value of the energy density delta rho over rho, where rho is the mean energy density in the box, and delta rho are the fluctuations with respect to this mean density. When this occurs, the regions of high overdensities collapse earlier than the matter radiation equality and form what's known as axion mini clusters. So they form self-gravitating bound structures of a mass of the order of 10 to the minus 11 solar masses. So this is an asteroid mass, and the radius of the order of 10th to 1 astronomical unit. So this is an asteroid spread over a volume that goes from the Earth to the Sun. Nevertheless, this typical density of the axion mini cluster is 5 to 6 orders of magnitude larger than the ambient dark matter density, which means that this is still a large enhancement over the dark matter that we experience in the solar system. These axion mini clusters have been studied in unbounded simulations. This is what I'm doing now with people in Grappa, University of Amsterdam. So we assume, for example, in our studies that we are dealing with two different profiles for the distribution of individual axion mini cluster, one being a power law, in which the energy density is proportional to the radius to some power. Particles that have an axion mini cluster that has formed through accretion, or NFW, which is corresponds to a mini cluster that has formed through hierarchical merging of smaller axion mini cluster. A simulation from late last year by Eggemeyer and et al. Actually follows the is an embodied simulation that follows the merging of individual axiom mini clusters, and actually shows that for the largest one, which is this circle here, made out of smaller individual axiom mini cluster, you you end up with a NFW distribution, at least in the outer skirt of the mini cluster itself. So our question is, how do axiom mini clusters survive the tidal disruption by the when an axiom mini cluster passes through a star which has with some impact parameter b. So this is the distance of least smallest encounter. The star has a velocity v. It deposits some energy delta E, which depends on the mass of the star, on the mass of the axiom mini cluster, on the mean square radius, which of the axiom mini cluster, which probes the inner distribution, which I said for us is either power law or NFW, and the velocity impact factors. So what we do is a Monte Carlo that basically takes for each encounter all of these parameters from random sampling from distributions. This is what I'm doing now with Thomas Edward, Bradley Kavanagh, and Christoph Weniger. Thomas Edward is now in Stockholm, Bradley Kavanagh is now in Santander, and Christoph Weniger is that the axiom mini cluster are distributed with an initial halo mass function that is obtained from the n-body simulation that I discussed before, that of Eggemeyer. And what we find is that the survival probability of axiom mini clusters as a function of the semi-major axis, so this is related to the distance of the orbit, the mean distance of the orbit of the axiom with respect to the galactic center. Well, we see that the more you move away from the galactic center, more the survival probability gets closer to 1, because there are less and less stars. So it's less and less probable that axiom mini clusters encounter any type of stellar object and get disrupted. Whereas as you move towards the center, this condition is no longer true, and within the kiloparsec axiom mini cluster are destroyed in any simulation that we consider. So blue here is power law, axiom mini cluster. Orange is NFW, and we consider both eccentric orbits. So this solid line is an average over all possible eccentric orbits that we consider, and circular orbits, which are dashed. We also consider axion radioastronomy. The fact that neutron stars possess a strong magnetic field that can lead to the conversion of axions inside of them. This is sort of what I discussed earlier. A magnetic field converts an axion into a pulse, into a radio signal. This is not done in the laboratory. This is done in the sky by the presence of the magnetic field of a neutron star. We consider here a Goldrake-Julian relation in which the neutron star is a magnetic field is modeled as a dipole. And you also get self-consistently the density of charges around the neutron star. This density of charges leads to a plasma frequency, and it can be shown that the axion photon conversion is possible when the plasma frequency is of the order of the axion mass. So within a narrow shell outside of the neutron star. There have already been results that constrain the axion photon coupling as a function of the axion mass for dark matter axion, converting in the magnetic field of individual neutron star. What we do is, instead of dark matter axion, we consider axion mini clusters. And instead of individual neutron star, we consider the population of neutron star in the galaxy and the interaction between neutron stars and axion mini clusters. So what we find...
Luca, 4 minutes.
Yeah. What we find is that for an axion of mass 25 microelectronvolt, these neutron star events are expected to be well inside the Earth orbit in the galaxy. And we expect that these are some of these events
Okay, is this a problem of Luca or myself?
I think a problem over Luca.
Okay. So Luca, sorry. Luca, can you hear us?
Miguel, I think you have to unmute Luca. Okay.
Sorry. So I got muted, but yeah, I finish here. So basically, what I want to say is that because of the quantum pressure, which comes, because of the fact that you want a particle in a box of size of that of a star, you end up with some velocity due to the Heisenberg uncertainty principle. So if you pack a boson inside a star, this boson has to have a minimal velocity due to the Heisenberg uncertainty principle. In an axion star, the pressure that comes from this velocity is enough to counteract the self-gravity of the star, not because it shines, but because it's in a equilibrium, hydrostatic equilibrium between the gravity of the ensemble of bosons and themselves, and the pressure which is not given by nuclear reactions, but by the Heisenberg uncertainty principle. If you balance these two forces, you end up with a mass for the axion star, which is inversely proportional to the radius of the axion star. So this is a one-parameter model that depends on the mass or on the radius of the star itself. This is what I studied in 2018 with Catherine Fries, Sebastian, now is in Stanford, Javier Redondo, and Frank Wilczek. We considered the radius rescaled in some units of the axion star as a function of the mass of the axion star. This is the regime that I discussed, this vertical regime, in which the mass is inversely proportional to the radius. This is true as long as you don't consider quartic self-coupling, which is this kink. When quartic self-coupling kicks in, then the whole equilibrium that I discussed is destabilized, and the axion star enter in a different regime. Okay, I think I will skip to the conclusions. I will not talk about black holes. So my conclusions is the sky as a laboratory for learning about new physics. In particular, we can keep an eye on the exotic like boson in the form of axiom mini cluster and axiom stars, which can lead to signals that are detectable in future surveys. Thank you for the attention.
Yeah, thank you, Luca. Thank you for the nice talk. We had some problems to follow part of your talk at the very end. Maybe you have an unstable connection, but anyways, I think if there are any questions on those slides, people can ask. Anyways, okay. So, are there questions or comments for Luca?
Hello. I would like to ask about the simulation part.
Yeah. Okay.
Yeah. First of all, how do you construct a stable halo that follows power law or FW profile?
So we okay. You mean for the mini cluster? We just modeled them as a power law or NFW. So the simulation that we do is not embodied simulation. So this simulation has already been published, and we're not part of that. We take the halo mass function that they find as the initial condition for our studies. So, so this Egemeyer 1911 is embodied simulation that follows how individual axiom clusters merge. What we do, and basically they come up with a halo mass function. So how an axiom cluster is distributed in mass, how the number density of axiom cluster is distributed in mass. What we do is take this as an input, and then we perform a Monte Carlo simulation that follows how a star injects energy into an axiom cluster. Now, it would be a different energy redistribution if this internal structure of the axiom cluster is power law or NFW. And this is where the density, the different density profile enters. But in general, if you, for example, if you consider power law, NFW, or any profile, you ask that the system is in self-equilibrium, so that it has to, the particle inside this object need to have the appropriate velocity distribution so that you attain such a profile. And we also take that into account. There are basically is once you're given the profile, you can say what the phase space distribution of the axons or of the particles are. Yes, and that's where we act in order to get the energy.
I see. So it's not embodied. And the second question is, do you have a comparison between the axiom mini clusters and the normal, say, WIMP part mini halos for such kind of comparison?
Yeah. So yes, yeah, it's not embodied because the embodied simulation was not done by us. We do a Monte Carlo simulation of what I discussed. For the mini halo, WIMP mini halo, if I remember correctly, they are related to the free streaming length of WIMPs, and so this is set by the kinetic decoupling of WIMPs. And this leads to mini halos that are generally more massive. So axiom mini clusters are expected to have a mass of order 10 to the minus 10 solar masses. Mini halos are expected to be order 10 to the 5 more massive It depends on the properties of WIMP, on the cosmology, but generally they are much more massive than Axiom mini clusters.
Okay, thanks.
I also have a question.
Yeah, please
Yes.
go ahead. Last question.
So you saw a plot for the probability of detecting actions, in particular string actions, in different experiments. Like the title of the slide was string actions, and I was just I'm just curious. I didn't understand what is the constraint that you imposed on the actions to tell that they come from string theory. I mean, it was very defined, exactly this curve. But what's the constraint that you're imposing?
We are imposing that the actions don't overclose. So we don't assume that the actions are the dark matter, but we don't ask that there's too much dark matter. And we ask that the bounds from Planck on isocurvatures are respected. And that's it.
But how do you distinguish that they come from string theory? What do you mean with
everything we demand? We basically we relate the mass and F, the decay constant of the axiom, to the string properties, to the soft supersymmetry breaking parameter. So we followed the paper by Svekt-Witten, which gives a rather general relation for the mass and F as a function of the soft SUSY breaking scale.
Okay, so it's based on a particular paper, I guess some string corner of Miriam Spetic and collaborators. Okay. Okay, just to know where it's coming from. Thank you.
Okay. I'll send you the paper. I'll send you the archive number.
Okay, guys. Yeah, thank you for the discussions, but it's time to move on now. So let's thank Luca once again. Thank you, Luca. Yeah, if there are more questions, of course, you are more than welcome to ask Luca during the discussion session at the very end of this morning. Okay, after the next talk. Okay, so let's go on in the agenda. The next speaker will be Javier Coronado Blázquez from IFT. Javier, are you around?
Yes, I'm around.
Yeah, thank you, Luca.
Yeah.
Okay, very good. Can you start sharing your screen and see if everything goes as planned? Yes.
Okay, can you see my
Very
slides?
good. Yes, we can
and
see
if
them.
I go to the next one, does it work?
Perfect. Yep,
yes,
seems to work. Yep. Okay, so please go ahead. You have 25 minutes.
Thanks, Miguel. And thank you very much to the organizers for inviting me to give this talk at this very nice workshop. So I'm going to talk about searches for dark matter subhalos among the gamma ray unidentified sources. So first of all, I would like to briefly introduce or motivate dark matter. I don't think it's necessary, but just a quick introduction. So our current understanding of the universe is within the lambda CDM framework, which contains a form of non-baryonic matter, which is responsible for structure formation, and it's 5 times more abundant than ordinary or baryonic matter, and it sums up to roughly 1/4 of the energy content of the universe. We have lots of dark matter evidence, namely the classic ones such as galactic rotation curves, the strong and weak gravitational lensing, and the cosmic microwave background anisotropies, but of course there are many more. Here are some of them. So over the years, we have proposed lots of dark matter candidates spanning more than 70 orders of magnitude in mass, ranging from extremely light particles such as actions, which have been just covered in the talk by Luca, or primordial black holes, which have been covered in the talk by Daniele, which are very macroscopic objects. And we're going to center on another very well motivated candidate, which are WIMPs, which are in this range of mass. So WIMP is an acronym standing for Weakly Interacting Massive Particle. These are thermally produced particles in the early universe, which they decouple from the plasma, and its abundance is frozen out. So the required cross-section of this process is very, very similar to that of electroweak interactions, and that's interesting. But it's more interesting that it naturally explains the dark matter abundance, and this is called the WIMP miracle. So it's a good candidate for dark matter. So this is the general picture we have on the left. The chi is 2 dark matter particles, WIMP particles, and here we will have 2 standard model particles going through an unknown interaction. So depending on how you read this diagram, you can have 3 strategies for search for this kind of particles. From right to left, you will have the LHC, which I think it will be covered by Iñaki on Friday. You have production. You collide standard model particles, and you hope to produce dark matter particles. If you read it bottom up, you will have direct detection, scattering of particles. There are many experiments doing this kind of search, namely Super CDMS or DarkSide, Gamma Libra. This Gamma Libra and Anais, they aim for an annual modulation on the dark matter signal, but the idea is the same. And we finally, if we read it left to right, we will have annihilation of dark matter particles into standard model particles. This is the case for indirect detection, and is the focus of this talk. So this process, you have this annihilation of particles, and you produce as byproducts many particles, namely photons, which will be gamma rays due to the mass of these WIMPs. You produce also neutrinos, which will be covered by the talk of Valentina on Friday also, and cosmic rays. Photons, these gamma rays are a photon channel, a golden channel in some sense, because they are not deflected by magnetic fields, such as cosmic rays, and they are much easier to detect than neutrinos, which is a very difficult to detect particle. And it's also interesting to know that there is no energy loss, at least at the scale relevant for these dark matter searches, which would be the local universe. So yeah, it's a good channel to look at. So we can have an Annihilation Cookbook, which would be this is the main recipe here. And we have many ingredients. We have, first of all, F is the gamma ray flux, the gamma ray data, which answers the question, what do we see in the sky, the high energy sky? Then we will have here the velocity average cross-section and the mass of the particle, but this is not really an ingredient in this cookbook. We will have then the J factor, which is an astrophysical factor proportional to the squared dark matter density. And this answers the question, how much dark matter and how is it distributed? It's a very interesting question to pose. And finally, we have N gamma, which is just the spectrum per annihilation, which answers how does dark matter annihilate? And this is a particle physics factor. So we will take a look at the first term here, the gamma ray data. We have to talk a little bit about the gamma ray astrophysics. Gamma rays are the most energetic known photons in the universe, with crazy, absolutely crazy frequencies and wavelengths. We have many types of observatories to detect them, mainly 2 types, space and ground-based. Example of a space-based telescope would be the Fermilab in operation more than 10 years ago. And ground-based is a Cherenkov telescope, which uses the Cherenkov radiation in the air. An example of this would be MAGIC, which is in operation since 2003. Both types are nicely complementary in things like sky exposure, energy range, resolution, etc. So it's very interesting to have both types operating simultaneously. Fermilab is an all sky telescope, so we can generate a beautiful image like this, which is the sky in high energy, basically, in gamma rays. And this is in galactic coordinates, meaning that this would be the galactic plane, the most intense emission. And then we have lots of points here. This map is very complex, actually, because it can be understood as many contributions. First of all, the galactic contribution is composed by inverse Compton, Bremsstrahlung, and pi-zero decay, which is a diffuse emission with a multi-component, which mounts up to the galactic emission, the emission which is coming from galactic sources. Then we have the point sources. We have galactic sources such as pulsars, supernova remnants, etc. And we have a lot, as you see, points here of extragalactic sources, mainly active galactic nuclei and other galaxies, radio galaxies mainly. And finally, we have an isotropic component, which would be simply the background, which is not resolved by the telescope, and then it's an isotropic background of gamma rays. And the question here is if we can accommodate dark matter in this picture. Well, to answer this question, we have to go to this second term, which is how much dark matter and how is it distributed, to understand if we can put it in the map. So a dark matter prediction would be a map like this. This is a dark matter annihilation simulated sky map. Is it possible to combine this and these maps? Is dark matter hidden in the gamma ray sky? Is this map hidden here? And most importantly, have we already detected dark matter? Well, this map is also complex. We have many things here. The most prominent source is the galactic center, where we have the largest amount of dark matter. Then we have the Milky Way halo and classic targets such as nearby galaxies, galaxy clusters, dwarf satellites, would be the classic dwarf spheroidals, the extragalactic background, spectral lines, which cannot be seen in this picture. And we are going to focus here on the dark satellites, the dark subhalos. And why are these interesting? Well, to understand the formation and evolution of dark matter halo, Milky Way halo, we have to rely on n-body simulations because it's a very nonlinear regime. And we have many dark matter simulations like this. This is Aquarius. This is a Milky Way-like halo, but okay, this is lots of dark matter, and the brightness is proportional to the density of dark matter. But where is our galaxy? So our galaxy, this is home, would be actually smaller than this. This is exaggerated. It's much smaller than all the halo that we have here. We have the virial radius at some point, which is defined by the order density. And we note that we have our galaxy here, but we would have lots of dwarf spheroidals, of dwarf satellites here, which would be the brightest spots, these very large spots. But we can ask ourselves what happened about the smaller yet very close ones. These ones would be the dark subhalos. Well, we use the Via Lactea 2 simulation and n-body simulation. And we have to take into account the low mass subhalo population. Why? Well, depending on the assumed dark matter particle, the wind particle mass, subhalos are expected to go down to 10 to the minus 12, 10 to the minus 6 solar masses. 10 to the minus 6 solar masses is the mass of the Earth. But this is impossible to numerically resolve due to limitations. Simply, this would be the subhalo mass function, this expression here, which is inversely proportional to the mass, meaning that the lower you go in mass, the more subhalos you have. So at some point it explodes and it's impossible to resolve. So this Via Lactea 2 simulation, we have a resolution of 5 million solar masses. Are we losing subhalos with still relevant J factors below? Well, the answer is yes. And to account for this, we can generate a repopulation of this original simulation by characterizing this Via Lactea 2 simulation and using some semi-analytical lambda CDM recipes of structure formation. And this allows us to push down the resolution limit down to 10 to the 3/1000 of solar masses, more than 3 orders of magnitude, which is very, very nice. So this would be this result. In the y-axis, we have the J factor, so it's the brightness, the larger the better. In the x-axis, we have the distance to the Earth in kiloparsecs. So again, the closer the better. And the color scale would be the mass of the subhalo in units of solar masses. So basically, we will have on the top corner of the plot, this would be the original Via Láctea 2 simulation at 5 10 to the 6 solar masses. We cannot solve anything else. And everything below it, this line, it would be our result, the repopulated Via Láctea simulation. So this would be the visible dwarf, massive enough to retain baryons and then to shine. But this would be dark satellites. This would be low mass subhalos, below 10 to the 7 more or less. They cannot host baryonic content and therefore are completely invisible, are dark subhalos. Yet they can be among the brightest ones. If you see here, 10 to the 19, for example, you have lots of dwarf spheroidals, very bright ones, but you have still lots of invisible dark subhalos with very, very relevant J factors, competitive with the dwarf spheroidals. So these subhalos, the dark subhalos, would appear in the sky as unidentified gamma ray sources, because as I mentioned earlier, they do not host any baryonic content and therefore are completely invisible in any other wavelength. They just emitting gamma rays due to the dark matter annihilation. And this is the same map I showed before of the Fermi-LAT, but attending to the class. And as you can maybe see here, approximately 1/3 of the detected sources are unidentified. They don't have any clear association. So maybe some of them are dark matter subhalos. So to take a deeper look into these sources, we have to define some filtering, some intelligent filters according to the expected dark matter emission. This is just to reject NIDs as potential candidates. There are these 5 source associations. This is trivial, of course. A latitude, because we don't want any source too close to the galactic plane, because as you saw earlier, the diffuse emission is very intense and it's very difficult to see something there. Flux variability, we do not expect the dark matter subhalo to show any flux variability over time, so we have a steady source. Then we use some machine learning algorithms to predict the class of the unidentified sources. And finally, multi-wavelength emission, as I mentioned, if you detect, for example, some emission in ultraviolet or infrared, you can reject this source as dark matter candidate. So this filtering turns out to be very, very efficient and very useful, because these are different catalogs of the Fermi-LAT collaboration. This column is the original numbers of unidentified sources, while the second one is the NIDs, the identified sources, compatible. We're not claiming that these are dark matter, of course. We say that in principle they're compatible with a dark matter origin. For example, this 3FGL catalog, which is a very famous one, we start from 1,000 unidentified sources, and we have just 16. So it's a very, very efficient filtering. Only 16 sources compatible with dark matter origin. And we have also to take into account the sensitivity, instrumental sensitivity to dark matter. This F-min, which is simply the required flux to have a detection over the background, is normally taken as the threshold flux of the catalog, which is a nice approximation, but is very, very naive, because there is an important dependence on the annihilation channel, on the source sky position, and the specific catalog or analysis setup. And intuitively, of course, one can see that a dark matter subhalo here, or any source at all here, would be much difficult to detect. It will require more flux to outshine the background, that one here, which is a very quiet zone in gamma rays. We compute this sensitivity, and the result is quite interesting, because this is, for example, for BB bar in this 3FGL setup, an analysis setup. And this is the flux in the y-axis versus the mass of the WIMP in the x-axis. And if you center in a latitude, galactic latitude, say 45 degrees, the red points here, the middle ones, you see that depending on the mass of the particle, the sensitivity of the Fermi-LAT varies more than an order of magnitude. So assuming a constant value, say 10 to the -9 here, would be a very poor approximation, and you will not take into account this huge variation of the sensitivity. Once you have this short list of candidates, you have also well characterized your sensitivity, instrumental sensitivity, you can perform a spectral analysis. The main advantage is that we have lots of data. We have 10 years of lab data by the time we did this analysis, while the catalogs and the sources were done with 4 or 5 years. So we are doubling the exposure. And we can favor or disfavor the dark matter hypothesis. We use the FermiPy software for this analysis. Basically, for each source, we are doing a point source detection map. Here you see clearly in the center of the region an excess, which is the source, more than 5 sigma detection. Then we will do a model of the region, in this case with photon counts. Here clearly is something there. And we can obtain the spectral energy distribution, the SED, here for a source, a very clear source. To do this spectral energy distribution, we can work with 3 astrophysical parameterization, classic ones in the field of high energy physics. A simple power law, which would be this form, a log parabola, which is a power law with a spectral curvature, and finally a super exponential cutoff power law, which is a spectrum very, very similar to that of pulsars and dark matter, by the way. And we can compute the preference of each model via a generalized likelihood ratio test. Generalized because we take into account the degrees of freedom of each model to take into account that. And this would be the traditional likelihood ratio test. So basically, we are computing this delta TS, test statistic. If this quantity is positive, is favoring dark matter. If it's negative, is disfavoring dark matter. Of course, even if it's positive, we would require at least delta TS larger than 25 to claim that we have positive detection or really take it seriously. Unfortunately, our best candidates have this delta TS at 10. So this is not strong enough to claim anything. Nevertheless, it's quite interesting to see that it follows very well this annihilation. This is annihilating to bottom quarks and this to the charm quarks. And as you see, this best fit dark matter spectrum nicely follows the points of the Fermi lat. So there are very interesting sources indeed, but still you will need something else to really claim that is dark matter. This is a table with lots of information. Don't worry about the best candidates we found. These 2 are the ones we have just seen, delta TS order 9, 10 for different channels. They point also to very low dark matter masses, wind masses, as the galactic center excess. And we have also another sources with a very low delta TS, order 2, 3 at most. This is not significant, relevant at all, but interestingly, they point to much larger wind masses, order 100, 300, even 600. So it's interesting, at least. And we are not trusting, of course, that these candidates are dark matter. So we can put constraints and limits to the annihilation cross-section here in the y-axis versus the wind mass, the usual plot. We have here the magic number, the thermal annihilation cross-section. And our work would be the black solid line here, which is competitive with the Planck data release 3 results of the CMB. And it's not quite away from the dwarf spheroidals, which is the purple one, the violet one in the bottom. And the left plot is for BB bar annihilation, and the right one for tau plus, tau minus as 2 benchmark examples. And it's also here, for illustrative purposes, the HESS, which is an Cherenkov telescope, limits on the galactic center. So yeah, it's competitive at least.
Yeah,
thank you.
5 minutes.
Okay, then we will move briefly to the spatial analysis. Once you have done a spectral analysis, you can also ask whether the subhalos have to show some kind of a spatial extension. The answer is yes. At least there are many papers here claiming that a spatial extension for a dark matter, for an identified source would be a smoking gun for dark matter indirect detection. We use our simulation to take a look to this. Again, this is the brightness, the J factor, versus the extension integrated up to the scale radius of the of each subhalo. And the color code is the mass. Well, you see that everything is pretty extended indeed. And this line here is important because it's the point spread function of the Fermi-LAT. This point spread function is similar to this picture here somehow, that even if something is point-like, if it's out of focus, you will not distinguish it from an extended source. You cannot see if this is extended or point-like. A similar thing happens in Fermi-LAT. Everything below this line, which is at 1 GB, sorry, would be point-like. This, even if it's 0.8 degrees, you will see effectively a point-like. But all this part, you will actually, in principle, see it as extended. And yeah, the most bright subhalos have to be extended, or at least we believe so, regardless of the mass, because here you have black points of 10 to the 3 and yellow points of 10 to the 7. So independently of the mass, you shall see some extension here. Nevertheless, we perform this kind of analysis over our best candidates, and they're all point-like. You do a likelihood ratio test, again, of the extended versus the point-like source, and the likelihood curve is monotonically decreasing. So there is no preference for extension whatsoever. On the other hand, here you see an extended source, which is not fitted to dark matter, just for illustrative purposes, which is clearly having a maximum in the likelihood, indicating that this has a clear preference for extension and a best fit value of 0.5 degrees. We are not finding anything like this in our best candidates. So this is a little bit in tension. Nevertheless, we are not discarding these sources as subhalos because more work is needed to understand the LAT sensitivity, not to point-like, but to extended subhalo. This work is actually being done, and we hope it's ready pretty soon. And in 1 minute, I would like to comment that this pipeline, this analysis can be easily extended to any other observatory. I talk about Fermi-LAT, which would be these dot dash green lines, LAT. This is the sensitivity versus the energy. And you see that the LAT is sensitive to very low, say, high energy photons. But then you have MAGIC, which I mentioned, HAWK, which I will mention very early, CTA, which will be the future of the field, which is currently under construction. And you see that if you take the Fermi-LAT, CTA, and HAWK, you are covering all the WIMP spectrum very nicely. Of course, in the case of CTA, we can only work with simulated data because it's, as I said, under construction. Extending the same analysis, we can reach to these constraints. The Fermi-LAT constraints will be these ones. I would like to stress also that they are competitive enough to actually probe the thermal values. Then in the middle, as one will expect, we have this preliminary, it's not published yet. We hope it's soon. CTA, the Cherenkov Telescope Array simulated data, which is competitive in the middle part. And finally, the HAWK data would be competitive at the largest, the heaviest WIMPs, the larger masses. And yeah, between these three observatories, you can basically cover all the WIMP range, which is very nice, actually. Yeah, summary and conclusions. Dark matter subhalos would be unidentified sources in the gamma ray sky, and they are independent probes. They are very nice to use. We need, on the other hand, N-body simulations to account for the distribution and brightness of dark matter subhalo. These subhalo candidates can be rejected or analyzed properly by applying a series of filters and then doing a dedicated spectral analysis. And this is basically all you can do. And the constraints are comparable and, more importantly, independent and complementary to other in the fields, and will be, of course, improved with more gamma ray data and future experiments such as the mentioned Cherenkov Telescope Array. So thank you very much for your attention, and I will be happy to take any questions.
Yes, thank you so much, Javier, for the nice talk. Okay, so we have the use of 5 minutes for questions or comments for Javier. So please just open your mic and talk.
Hello?
Yep.
Hello. Yeah, so I have 3 questions to say. First, Do you use an Ernesto profile or NFW profile to calculate the J factor?
We are using an NFW profile in the repopulated simulation because it's in the Via Láctea 2 simulation. It's what we see. On the other hand, in Aquarius, in principle, it's better to add a NASTO one, but we want to be consistent with what we see in the simulation.
Okay, then how do you determine the concentration parameter?
Yes, it's in the backup. It's very nice to ask. Thank you. We use this Molinet et al. Mass concentration parameterization. So basically, the J factor is proportional to the cubic concentration, which is C200 here. And as you see, the lower the mass is, the larger the concentrations, and the nearer the galactic center, the larger are the concentrations. So this also motivates that the dark subhalos are very nice targets because they are near the galactic center and they are low mass. So the J factor is very competitive. So we use, this Molinet et al. Parameterization. Here is the reference.
Okay, and is it useful to just stack all the unidentified sources that you find and see whether they are extended or not? Because it's also possible that the outside of these sources, they are just too weak to be identified.
Yes, that is precisely the kind of work we are working on, and we hope to publish it very soon. So we cannot say anything yet. Sorry.
Okay, then one more comment that might be useful for you, because for either the concentration mass relation and also the very low mass subhalos, you can already find those things in real simulations. I think those simulations are done by Professor Wang Jie from National Astronomical Observatory of China. They have performed the zoom-in simulations, and their resolution can go down to 10 to the minus 6 solar mass. So you can ask for those simulations.
Okay, thank you. I will take a look. Thank you very much.
Sorry, but is this, if I can comment, is this for redshift 0? Because of course there are some other simulations out there, no, where they resolve microhalos, even Earth-like microhalos, right? But this typically stops at redshifts of the order of 25, 30 or something like that, right? Because after that epoch, it's very, very, very difficult to model and to follow, to track the evolution and the merging of all these little ones, right?
Yes,
so are you talking
I think some of those simulations they perform more goes to redshift 0. So you can ask for more details if it's useful.
Okay. And you are talking about subhalos too, right? Not only halos.
Yeah, subhalos. Yes.
Okay. That will be very interesting for us, of course.
Yeah, thank you.
Thanks.
Okay, so more questions. Maybe Sven, I see your camera.
Yes,
Sven, do you
yes, I want to ask a question. At some point, you were showing a table with possible candidates and the evidence or not evidence for dark matter. And you also had always a range of the dark matter mass there. Maybe you said it and I missed it, I didn't understand it, or So how do you determine exactly the mass with its uncertainty? I mean, it's a bit funny that you always have this clear value with a relatively small uncertainty, but at the end you don't have evidence for dark matter, and they're also incompatible with each other. So I don't know what to make of it.
Yes, it's a good question. Well, of course, first evidence for these sources being dark matter subhalos, it would be that they are compatible between them, because dark matter should be universal, of course, and this is not happening here at all. So yeah, this is clearly saying something. Yeah, we determine the mass fitting the dark matter, the spectral energy distribution of the Fermi-Lat data. These black points are just the data as Fermi-Lat sees. Yeah. And then we perform a fit looking for different dark matter masses, different annihilation channels, and this is the best fit value. So here, as the points have a relatively small uncertainty, the uncertainty in the spectrum will be also small. This gray band, I don't know if you can see it very well, is the uncertainty, actually. And basically, this is why most of these sources have a very small uncertainty. There are some that not, of course, you have here, I don't know, 48 plus minus 13. This is, of course, a larger uncertainty than 11
Yeah,
plus
but
minus
others are
13.
pretty tight, yeah, 10% or so. And
yes. But it comes from here, from just fitting the lat data, the Fermi lat data.
Okay, it still looks a bit strange to me that there's no evidence for dark matter. Still, you have a good fit to the mass. Yeah, I would expect that you may have a central value, but then the uncertainties, because you actually are not sure that you see dark matter, would be so large that also, I don't know, 0 would be compatible or something like this. But it's probably too naive what I'm thinking.
No. It's a very good point. But the thing is that there is a class of objects in the sky which are very similar to dark matter, which are pulsars. Pulsars in gamma ray have a very, very similar spectrum, very similar. And they peak at roughly 1 GeV. So these sources could very well be pulsars. Still, they are not. They have not been discovered as pulsars. So it's very difficult to disentangle this dark matter pulsar confusion. Very difficult.
Okay.
So this is probably why we find a good fit to dark matter in these sources.
In case you're interested, I put the related link in the chat board.
Okay. Yeah, thank you. We'll take a look. Okay, guys, I think we should stop here, at least formally, okay? I understand from the organizers that we have extra time. We have plenty of time to discuss in this same room. So you are more than welcome to stay if you want to, okay? But let's formally finish the day here. So thank you everyone for your attention, and also thank you the speakers for the nice talks. So, okay, formal end and now informal beginning for the discussion. So we can just continue with the same kind of discussions if you want to. So are there more questions? I take the freedom to ask once again. Are there more questions to the speakers, either to Javier or Luca, for instance?
Yeah. So Javier, I have a very naive question about the baryon effect. So like some missing satellite problem. So is there, so simulation doesn't include, of course, baryon, right?
No, it's a dark matter only simulation, yes.
Yeah, so is there any effect of the baryon, especially for such a low mass subhalo, I mean, to modify the J factor?
Yes, this is a big caveat of the work, because the answer is that we don't know, because there are contradictory explanations in the field. Some works claim that the baryonic component will deplete the abundance of subhalos. Other works, such as Van den Bosch, for example, claim exactly the opposite, that baryonic will enhance actually the structure of the dark subhalos, making them very, very resilient and therefore very dense. So yeah, it's something we have to tackle, but the answer is that we don't know which would be the result, in which way it would go.
I see.
Yes, and also regarding to the baryon that raised here, for the mini clusters of axioms that which are very close to the center of the halo, then it will have very high inference from the disk for stars, which inside of size of 10 kpc, then the tidal disruption from the disk will be even stronger than the halo itself. So we might also need to take into account those inferences, especially when the orbits are very close to the center.
Yeah, there is a paper indeed by, well, there are a few papers indeed by James Bullock group from Irvine, right? And they actually play with all this by running some hydro simulations to address actually this issue, about the subhalo survival in the inner parts of the galaxies, galaxies like our own. And they see a factor 5, more or less 5 to 10 decrease in the number of subhalos within the inner, I think it was within the inner solar galactocentric radius. So something like 10 kiloparsec. So they see a huge decrease of subhalos, of number of subhalos, as you mentioned. But also, as Javier said, there are other works that actually claim that the structure of subhalos will be so compact that even if they lose a lot of material in the outskirts, they will still retain the small spikes in the very center, right? High enough to give us annihilation signals that will be in principle seen by our instruments, or in principle, or potentially detectable by our instruments. So this is something that, as Javier said, we are really working on now, and we have also some plans to attack this problem from the embodied simulation side together with Hydro. Yeah. So yeah, it's really a hot topic in the literature right now, I would say.
Yeah. So I have some question for Luca, if you can answer.
Yes.
Yeah. So in your slide of survival or actual mini cluster, so the shape, could you show your slide?
Sure. 1 second, because I closed them. Let me go back. I'm there almost. 1 second.
I can share. I can share.
Okay, very good.
So just a very naive question. So maybe some sharp change happens around some 0.1 kiloparsec or something like that. Is there any, I mean, so what make some shape? I mean, or so is there any special for kiloparsec, or I mean, why the shape is not like this one or not like this one, but big change around this one?
Yeah. So okay. Well, the dotted line here, the vertical dotted line, is where we are. Is the position of the solar system, 8.3 kiloparsec. We see that basically where this disruption occurs depends on the density profile of the Axiom mini cluster. So a power law is steeper than NFW, so it's more difficult to disrupt it. This is why it occurs for inner orbits where the stellar density is higher. In general, it occurs, this order 1 kiloparsec scale because of the density of stars. It starts becoming important in the more you move towards the galactic center. So the way we model our galaxy is through a bulge, disk, and a halo component. The halo component does not really affect the distribution, whereas the disk component starts getting important. Remember that we also have stars in the disk, so they have a sort of cylindrical symmetry, whereas the dark matter halo is spherically symmetric. So what we see here is an average over all possible orientation of the Axiom mini cluster orbits. So if an orbit of our Axiom mini cluster lies exactly on the galactic plane, it gets more easily disrupted, and Axiom mini cluster they have tilted orbits. They only spend a fraction of their time inside the dense disk.
Okay.
So why is it kiloparsec? I would just say because of the distribution of stars that gets denser within the solar the position of the solar system.
The density of stars, yes, probably right. So look, I mean, regarding this stellar component, How do you model the velocities of these stars? Are they frozen somehow, or do you really provide velocities to the baryonic component?
They are co-rotating. We assume that actually co-rotation is also important. Like if a mini cluster rotates in the same direction, similar to with a velocity similar to that of a star, it gets more disrupted than if you neglect this type of correlation.
Yeah. Okay. That's why.
Yeah. So we realize the star, and we realize the Axiom mini clusters.
So I actually have a question for you, if I can. I don't know if Chang already finished, but I may have a question also for Luca. So regarding these mini clusters, what was the role that they could actually have in the structure formation? I don't really see the connection between these mini clusters and the way structure formation works to end up with this filamentary structure, web that we have, and all the structures that we see at redshift 0. So what was the role of these mini clusters in all this?
I don't think they play any role because so these are sort of substructures that are too small to imprint anything which is visible in the CMB. And above this mini cluster scale, axons are called dark matter. So any dark matter simulation that is not able to resolve this axiom mini cluster scale would look as a cold dark matter simulation.
I see. Yes.
The analogy that I have is that of fuzzy dark matter. So for fuzzy dark matter, you see these cores at the galactic scale, but that's because the fuzzy dark matter is much lighter, so it has a wavelength, debris wavelength, which is of astronomical scale. Axion stars, in this case, that form inside axion mini clusters and have a similar, slightly smaller scale, would behave the same. So if you were able to do a QCD axion simulation down to that scale, you would also see that those type of structures. But of course, this is mean zooming several times to reach this scale.
Yes.
I appreciate this.
Now I get it. So these mini clusters will be just above the cutoff in the MATE-POW spectrum,
Yeah,
or something like that.
Exactly. Yeah.
Okay.
But at a very high K.
Yeah. Well, the effective mass that you mentioned was something like 10 to the minus 12 or something like that, or even less. So solar masses.
Right. Yes.
Yeah. Okay.
Are those mini clusters actually very abundant?
This is so. This is what simulations are trying to assess. So, in simulation, you see order 10% of the dark matter to be in clumped structures. So if you take all of the dark matter and if you take 10% of the galaxy dark matter and you bind it in sequestered in structures are bound and have the properties that I mentioned, these could be of order 10 to the 22 objects. But this is a parameter in the theory, basically, which is not well understood.
Then essentially, will they put some quite effective impact on star streams? Like the star streams might be just the crossover by these mini clusters, like bullets again and again, and they will get broadened.
But this is what we're trying to do with our Monte Carlo. So we're trying to understand how how often an axiom mini cluster interacts with a star or with the Earth, and it seems that like they are more or less not very much affected by the presence of stars, at least near the solar system.
Yeah.
Was that the question?
That makes sense, right? Because the densities are very low, no, inside these objects. So that makes sense. And regarding that, regarding the modeling of the internal structure of these mini clusters, why do you assume power law or NFW? Is there any reason beyond just starting with something? Is there really any good reason to expect this also for mini clusters, for axiom mini clusters?
Well, power law is what you get when you study accretion of dark matter on for example, a black hole. So when you accrete mass, you expect a power law behavior. NFW,
index, right?
The 9/4. Yeah. Yes.
Yeah.
We just followed some reference on this. Whereas the NFW is because this is expected for the largest one. Like those that are formed later in the matter dominated universe out of merging of smaller ones. So I expect that the reality is in between the two. Like the smallest one are formed directly around matter radiation equality with some power law profile, and then they start to hierarchically merge.
As you say that those, especially the central part of the mini clusters, are dominated by equilibrium between quantum pressure and gravity, then we should think that actually their density profile should follow solitone rather than FW power law.
Right. Exactly. But this is is only in the inner part. I agree. I agree. It's a the idea is that in the inner part of these axiom mini clusters, the quartic self-interaction of like axiom-to-axiom scattering cannot be neglected, and this cools off the axions inside this dense region, and that's where the solitone forms. So that's where the axiom mini cluster forms.
So I'm a little bit confused the concept of the axiom mini cluster and axiom star. So they are definitely different in your context, or?
Yeah. So for axiom star, I mean this quantum mechanical object, basically, in which the pressure is given by quantum pressure.
Yeah.
It's really given by the fact that you have a particle in a box. So you don't know how fast it moves. So you have some velocity associated to its uncertainty in the position. Whereas for axiom mini clusters, this is a classical field, and you give it some
coherent motion. So my question was,
right.
so because Jiajun's question is more about axiom star, I think, not the axiom mini cluster. Isn't it true? Or?
But in the central, they are the same.
Central.
Can you repeat the question? Sorry.
I mean, I thought that.
Understand.
I thought that Jiajun's question is it's about action star, not action mini cluster. Just in my thought, is it true or?
I missed the word. Like, what is about action stars? The visualization.
So Jiajun, I also forget. Jiajun case is about some quantum pressure and gravity balance. Is that correct?
Yes.
Yeah. So
That
that
applies
okay.
to boson star, but it also applies for the central part of mini cluster.
Yes, exactly. Yes, I agree.
Okay.
Yeah. There are a couple of simulations that follow this formation of the solitonic core inside Axiom mini clusters.
Okay. I see. So I think time is already past the official time of discussion. So maybe it is good to finish this discussion, right?
Okay. Yeah.
Yes.
I agree. Just a comment, Yejun, about the paper that you posted. I knew the paper. I didn't remember the first author. This is the paper also with Carlos, Frank, and Simon and Volker, and all those, right? But this is for main halos, no? If I'm not wrong. And that's why we are most interested in subhalos, no? For obvious reasons. But anyways, it's a great work. Of course, it's in Nature. And well, it's a new era. Okay, good. Yeah, thank you guys for all the discussions. I really enjoyed them. Yeah, so I leave my Korean colleagues to close maybe.
Yeah, I will do that. Yeah. So then have a nice lunch. Okay, and also
Thanks.
dinner. Okay, so then see you tomorrow.
Bye-bye.
Bye-bye.